Assalamualaikum dear students. In this lecture, we will be discussing differentiation and integration properties of Fourier representation. Okay. Now see the effect of differentiation and integration. It may be considered with respect to time, with respect to time for a continuous time signal, or it can be considered with respect to frequency for a Fourier transform and discrete time Fourier transform signal. Or discrete time Fourier transform series. So first of all, let us first discuss differentiation in time. Let us consider an effect of differentiation on a non-periodic signal. Okay? So we will consider a non-periodic signal x of t, and we'll consider the effect of differentiation on non-periodic signal x of t. Okay. Uh, Firstly, we know that inverse Fourier transform that inverse Fourier transform of a signal x of j omega it is given by x of t. Okay, so x of j omega is Fourier transform of x of t. So we have something like this. If we take Fourier transform of x of t, we will be obtaining x of j omega. If we take inverse Fourier transform of x of j omega, we will obtain x of t. So inverse Fourier transform, this is inverse Fourier transform of x of t. So inverse Fourier transform of x of j omega will give me x of t, and it will be equal to 1 by 2 pi. This is the general formula, integration from minus to plus infinity x of j omega e raised to power j omega t d omega. Okay. Now if we differentiate it, differentiating above equation both sides, if we differentiate above equation both sides, we'll be having d by dt of x of t, d by dt of x of t, it is equal to 1 by 2 pi integral minus infinity to plus infinity, then x of j omega, then differentiation of e raised power at with respect to t, it is a e raised power at. So we have j omega e raised power j omega t, then d omega. Okay. From which it follows that d by dt of x of t, it is equal to d by dt of x of t, it is equal to, or I can write it down like this. If I take a Fourier transform, if I take Fourier transform of this, it will be equal to j omega times 1 by 2 pi x 1 by 2 pi integration minus infinity to plus infinity x of j omega e raised power j omega t, then d omega. Okay. D omega. So which is nothing, I can conclude that once we take Fourier transform of d by dt of x of t, I will obtain j omega times x of j omega. okay, j omega times x of j omega, j omega times x of j omega. Or I can also write it down, because why? Because x of t, if we take Fourier transform of x of t, we will obtain x of j omega, x of j omega. Therefore, thus, if we take Fourier transform of d by dt of x of t, is equal to j omega times x of j omega, x of j omega, x of j omega. So this is the general form. If we take differentiation of a signal, then its Fourier transform will be j omega times uh, the Fourier transform of the signal which is being obtained without differentiation. Okay? Which is being obtained without differentiation. Now, if we have examples like this, let us solve an example. Say, for example, we have an example, find the Fourier transform of d by dt of e raised to power minus at u of t. We have to find Fourier transform of differentiation of e raised to power minus at ut. Okay. Now see, we know that what is d by dt into e raised to power minus at ut equal to. Okay. So we will apply product rule for differentiation. Okay. Using product rule for differentiation. So we can write down what is product rule. Product rule is d by dt of u into v. It is equal to d by dt of u into v plus u into d by dt of v. Okay, that is the product rule. So therefore we can write down d by dt of e raised to power minus at ut will be equal to minus a times e raised to power minus at, okay, and u of t plus e raised to power minus at differentiation of ut is equal to delta of t. It is equal to delta of t. This is equal to delta of t. Therefore we can write down d by dt of e raised to power minus at u of t will be equal to, then it will be equal to minus a e raised to power minus at u of t plus, now see, any signal multiplied by impulse function, any signal x of t multiplied by an impulse function gives us an impulse function. Okay, if it is defined at t, if it is defined at t, we have already mentioned it. So this will be here delta of t. Okay, this will be delta of t. So this will be delta of t. Just a second, this will be delta of t. It will be delta of t. How? Refer to convolution discussion. We have already discussed it when we were discussing convolution sum and convolution integral. Okay. So now see, if we taking Fourier transform of above equation, taking the Fourier transform of each term each term, and using using linearity linearity we may write, okay, we may write, see, if we'll take now Fourier transform of each term, so we will have to take Fourier transform of d by dt of e raised to power minus at ut. Its Fourier transform will be equal to Fourier transform of Fourier transform. Yes, its Fourier transform can be written as, what is the Fourier transform general equation? Minus infinity to plus infinity. Then we'll take Fourier transform of, we have expanded it here. Okay, we have expanded it here. D by dt of e raised to power minus at ut is equal to, by applying the product rule, we have separated the terms. So we'll use those terms here. So we know that then it will be equal to minus a e raised to power minus a t, then you have u of t, u of t. Okay, this is the general formula of Fourier transform. X of t, Fourier transform of a signal x of t is equal to uh, integral minus infinity to plus infinity. Okay, then x of t e raised to power minus j omega t dt. Okay, dt. So that is the first part. The second part, which was obtained from product rule, it is minus infinity to plus infinity, that is Fourier transform of delta t, Fourier transform of delta t. So basically we are taking the Fourier transform of this equation now. Okay, this is a simplified version of this equation. This is a simplified version. So we are taking Fourier transform of this equation now. Whatever we have obtained using product rule, it is a simplified form of e raised to power minus at ut. So now we will have minus infinity to plus infinity, then delta of t e raised to power minus j omega t dt. Okay, so this is one portion of the signal, and this is another portion of the signal. Okay, this is another portion of the signal, and we are basically taking Fourier transform by applying a general formula on both these parts. So there are two different parts of the signal. One is this part and another is this part. We are taking them separately and applying linearity principle. Okay. So can be Fourier transform can be written then. It will be equal to, see, minus a is constant. We can take it out. Then we will be having minus infinity to plus infinity. We are left inside with e raised power minus, you have a plus j omega, t, then dt. U of t is equal to 1. U of t, because it is a unit step function, it is equal to 1. And if we apply u of t equal to 1, then our limits will also change. Okay, our limits will change from 0 to infinity. Why? Because u of t, it is defined from 0 to infinity, and its magnitude is equal to 1. Okay, plus um, plus what is integration of delta of t? What is Fourier transform of delta of t? Fourier transform of delta of t impulse function is always equal to unity. It is equal to 1. We have derived it many times. Okay, now we can further write it down. That means Fourier transform of d by dt of e raised to power minus at u of t, it is equal to now. So integration from 0 to infinity of e raised to power at, integration of e raised to power at will be equal to e raised to power at divided by a, e raised to power at divided by a. So if I solve the integral, it will be equal to minus a divided by minus a plus j omega, a plus j omega, and inside you have a plus j omega. Then this is applying limits. You will have limits from 0 to infinity, and then you have plus 1. Okay, plus 1. Now see, you have a negative sign at the numerator and negative sign in the denominator, and they will be cancelled out. So we will be having now uh, Fourier transform of d by dt of e raised to power minus at ut will be equal to a divided by a plus j omega into e raised to power minus infinity. E raised to power minus infinity will be equal to 0. E raised to power 0 is equal to 1. So it will be 0 minus 1 plus 1. Okay. Therefore, we can write down it will be equal to minus a divided by a plus j omega plus 1, which can be written as minus a plus j omega divided by a plus j omega. A plus j omega. Okay. Now see, you have plus a here, you have minus a here. They will be cancelled. Therefore, we can write it down. It will be j omega divided by a plus j omega. Hence, we can say Fourier transform of d by dt e raised to power minus at u of t will be equal to j omega divided by a plus j omega, a plus j omega. This is the Fourier transform of e raised to power minus at into u of t. We have now another question. For example, we have another example now. Say, for example, we have another example now. The question says, find the Fourier transform. Find the Fourier transform of x of t. Fourier transform of x of t equal to e raised to power minus 4 mod of t. Minus 4 mod of t. Now see, Fourier transform of x of t. Fourier transform of x of t will be equal to x of j omega. Fourier transform of x of t will be equal to x of j omega, and x of j omega will be equal to applying general formula of Fourier transform, minus infinity to plus infinity. Then you have x of t, then you have e raised to power minus j omega t dt. Okay, and here our x of t is equal to e raised to power e to the power minus 4, then mod of t, then e raised to power minus j omega t dt. Okay, this is what is there. And if we simplify this, mod of t means t having either positive value or negative value. Okay, t having either positive value or negative value. When t will be negative, when t will be negative, when t, let us, so mod of t, I'll write down here, mod of t means t having positive or negative value. Okay, positive or negative value. So when t will be negative, we can write down x of j omega can be written now integration of e raised to power minus 4. Then if t will be negative, then it will be equal to minus t. Okay, it will be equal to minus t, e raised to power minus j omega t dt. When t will be negative, then its limits will be from minus infinity to 0. What is the another part? T can be positive also. E raised to power minus 4, then plus t positive t. Okay, positive t. So if t will be positive, then you have e raised to power minus j omega t, then dt. When t will be positive, the limits will be from 0 to plus infinity. 0 to plus infinity. Okay. So we can simplify this. This will be equal to minus infinity to 0, e raised power 4 of t, e raised power minus j omega t dt, plus 0 to infinity, e raised power minus 4t into e raised power minus j omega t dt. Okay. And this will be now minus infinity to plus infinity. Bases are same, powers are added, e to the power 4 minus j omega t dt, plus 0 to plus infinity, e to the power minus 4 plus j omega t dt. Okay. And now see, integration of at, it is equal to integration of e raised power at. Okay, integration of e raised power at, it is equal to e raised power at divided by a. So if I will integrate it, I will be having 1 by a, that is 4 minus j omega, 4 minus j omega into e raised power 4 minus j omega t. Then what are the limits? It will be 0, it will be 0 and minus infinity. These are the limits. Then second part, if it will be integrated, it will be equal to e raised power minus 4 plus j omega t divided by minus 4 plus j omega, and this is 0 to plus infinity. 0 to plus infinity will be limits. Okay, 0 to plus infinity will be limits. If we simplify them, we'll be able to find that we have here e raised power 0 is 1, e raised power minus infinity is 0. Okay, so we'll be applying limits. We'll be having 4 minus j omega, 1 divided by 4 minus j omega, plus minus 1 divided by minus 4 plus j omega. Okay, now see, you have something negative sign in the numerator and negative sign in the denominator. So we can simplify it. It will be written as 4 plus j omega plus 4 minus j omega divided by a plus b into a minus b. It is equal to a square minus b square. A square minus b square. Okay, a square minus b square. So this is what we'll be having. In the numerator, you have plus j omega and minus j omega. They'll be cancelled. Then we'll be reduced to 8 divided by 16 plus omega square. Why? Because j square will be equal to minus 1. J square is equal to minus 1. Or, okay, this is what is the result now. Therefore, Laplace transform of, okay, therefore, sorry, Fourier transform, not Laplace, Fourier transform of e raised power minus 4t, it is equal to 8 divided by 16 plus omega square. Okay, 16 plus omega square. Similarly, I have another example. Now, there is another example which asks that find the Fourier transform of signal x of t equal to d by dt of e raised power minus 2t. This is the Fourier transform now of a differential of e raised power minus 2t. So previously we were trying to find out the Fourier transform of e raised power minus 4t. Now this is the differential form of the exponential function. So it is a different one. Okay. Now see, we know if x of t is equal to d by dt of e raised power minus 2t, t can have positive values and t can have negative values. So we can write it down, then this signal could be written as d by dt of e raised power plus 2t plus d by dt of e raised power minus 2t. So this is when t is negative, okay? And this is when t is positive. T is having positive value. So it can be composed of two terms when one is with t having negative value, another one is with t having positive value. Now see x of j omega, Fourier transform of x of t, Fourier transform of x of t, it is equal to x of j omega. What is x of j omega equal to? X of j omega is equal to integration minus infinity to plus infinity. Then x of t e raised to power minus j omega t dt. This is the general form, okay? General form. So in our question, in our context, x of j omega will be equal to, it will be a Fourier transform, Fourier transform of uh, Fourier transform of d by dt of e raised to power 2t, okay, plus d by dt of e raised to power minus 2t, okay, or it will be Fourier transform of twice e raised to power 2t, okay, plus minus 2 e raised to power minus 2t, Fourier transform of these two terms, okay. So if we apply general form here, then x of j omega will be equal to, it will be equal to 2 times when t will be positive, our limits will be from minus infinity. When t will be negative, our limits will be from minus infinity to 0. Then you have e raised to power, e raised to power, uh, sorry, we'll write down here 2 times e raised to power 2t, then e raised to power minus j omega t. This is the general form, dt. What about the second part? It will be when t is positive, our limits will be from 0 to infinity. Then 2 times e raised to power minus 2t, okay, then e raised to power minus j omega t dt dt. So this is how the Fourier transform can be found. Therefore we can write down x of j omega will be equal to 2 limits from integration of limits from minus infinity to 0, then e raised to power 2 minus j omega t dt plus minus 2 integration from 0 to plus infinity, okay, then e raised to power minus 2 into uh, sorry, it will be 2 plus j omega t and dt. If we integrate it, we'll be able to find, we will have 2 divided by 2 minus j omega, because integration of e raised to power at is equal to e raised to power at divided by a, okay. Then you have e raised to power twice 2 minus j omega t. Then we have limits are from minus infinity to 0, then minus 2 divided by minus 2 plus j omega, 2 plus j omega, then you have e raised to power minus 2 plus j omega t and its limits will be from 0 to plus infinity, okay? 0 to plus infinity. Now see, we have a negative sign in the numerator and we have a negative sign in the denominator. They will be cancelled out, okay, they will be cancelled out. Okay, all right, so let me just check it. So we had here, I have made a mistake here. We have minus 2 here, minus 2 here. So that is what came out. Okay, this is fine now. Now, this means that we can simplify the equation 2 minus 2 divided by 2 minus j omega. Then we have e raised power 0 will be equal to 1 and e raised power minus infinity will be equal to 0. Okay, it will be equal to 0. Then we have plus 2 divided by 2 plus j omega, and e raised power minus infinity will be equal to 0 and e raised power 0 will be equal to 1. Okay, so this will simplify us now. Our problem will be simplified now. We can rewrite this. It will be equal to 2 divided by 2 minus j omega minus 2 divided by 2 plus j omega. Okay, 2 plus j omega, which can be further written as 2 into 2 plus j omega minus 2 into 2 minus j omega divided by 2 minus j omega into 2 plus j omega. 2 plus j omega. Okay. Now see, in the numerator, once we simplify it, we'll be having 4 plus 2j omega minus 4 plus 2j omega, and in the denominator we'll be having a plus b into a minus b will be equal to a square minus b square minus b square. So in the numerator now you have plus 4 and minus 4, they'll be cancelled out. We'll be having then 4 plus j omega divided by 4 plus omega square. Now see, therefore Fourier transform of d by dt of e raised power minus 2t minus 2t. Okay, this is my question now. So this was my signal. It is equal to 4 times j omega divided by 4 plus omega square. Okay, 4 plus omega square, and this is its answer. This is the answer of the problem. Okay. Similarly, this was differentiation in time. We can similarly have differentiation in frequency also. Okay, so let me conclude it here. We can also have differentiation in frequency. We can have differentiation in frequency. Say for example, if we have a signal x of j omega which is in frequency domain, and it is equal to integration, which is basically a Fourier transform of x of t, which is equal to, in its general form, integration from minus infinity to plus infinity x of t e raised to power minus j omega t dt. Okay, if we differentiate above signal both sides, what will be we having? D by d omega, we are differentiating with respect to frequency, of x of j omega will be equal to integration minus infinity to plus infinity j of t, not omega, sorry, it is j of t minus j of t into x of t, then we have e raised to power minus j omega t. So differentiation of e raised to power at will be equal to a into e raised to power. So I'll write down here d by dt of e raised to power at, it is equal to a e raised to power at. So we'll be having now dt here. So this is differentiation from which we can say it follows that minus, see, d by d omega of x of j omega, it is equal to okay. So this is basically Fourier transform. Okay, this is Fourier transform. We can relate it to the general form. If we have a look on equation A, we can see that on the left hand side this is Fourier transform. Okay, on the left hand side this is Fourier transform. Fourier transform like we have here. Similarly, on the left hand side this is Fourier transform. In equation A and equation B is here. In equation B, we can say x of j omega is the Fourier transform of a signal, which is x of t. Okay, x of t. And in equation A, we can say it is a Fourier d by d omega of x of j omega. It is a Fourier transform of a signal, which is minus j t x of t. Okay, because if you see, this is the input signal here, and here you can correlate A and B. You can see that this is the input signal here. Okay, therefore we can say if we take Fourier transform of minus jt x of t, okay, if we take Fourier transform of this signal, we will be having d by d omega of x of j omega. Okay, x of j omega, x of j omega. So this is basically signal. This is basically signal. Why is this true? Fourier transform of minus jt x of t, its Fourier transform will be d by d omega x d by d omega of x of j omega, because x of t, if you take Fourier transform of this, you will be having x of j omega. Okay, x of j omega. Same thing was true here also. Same thing was true here also. By similar logic, I had, you know, d by dxt is basically inverse Fourier transform. Inverse Fourier transform of a signal. Okay, inverse Fourier transform of a signal. What is the signal? Signal is this much. Okay, this is inverse Fourier transform. Inverse Fourier transform of a signal. This is inverse Fourier transform of a signal. Or in general, we can say this is Fourier transform in this direction. If we will take Fourier transform of this d by dt of x of t, and in reverse side you will perform inverse Fourier transform, and both of them are Fourier transform pairs. Fourier transform pairs. Okay, both of them are in Fourier transform pairs. We'll be now discussing integration property. Integration property. We'll be discussing integration property. Integration property will be discussed in our next lecture.